Don't get too excited about those kids. Okay, let's start. So like I say, really impressed. You put last year's cohort to shame, and it looks like we're going to achieve quite a lot this term. So let's make sure you can come along, and I think you'll be quite surprised what we can do in the 10 weeks that we've got. I don't normally touch on this until week 2. I just want to give you a little bit of food for thought. So, you often hear it called capacitive reactance, inductive reactance, but we've got this word reactance. What does reactance mean? Anyone? You can sum it up pretty quickly next to you if you've heard it before in your life. Reactance is... Second? Yes. Probably an easier way of just saying it is AC resistance. Now this is, we need to be careful when we say AC resistance, because it only has that resistance at one frequency. So if we've got a capacitor, and a capacitor just looks like 2 parallel plates, it's exactly what it is, there's no mystery attached to it, that's what it is. 2 metal plates that are close together. They might be wound up in a special way, or they might have crystals in them or whatever. But that's all they are, is this. It's a gap. It's a gap. You've got this, which is a coil of wire. Now if I say what's the resistance of the capacitor, what's the resistance of the inductor, that's a meaningless question, right? Because there is no resistance, there's only reactance. Well, there is some resistance in there, but don't neglect that. But for all intents and purposes, we only have this, we do not have this. We have reactance. And for this, it's called X for the AC equivalent resistance, if you like. So XC, in other words, the resistance of a capacitor, the reactance of a capacitor, 1 upon 2 pi FC. Where did it come from? To derive it, it's on the web pages if you want to see it. Let's not fill your head with too much stuff at this point in time. So XL is the inductive equivalent, and that is 2 pi FC. Notice it's the same, it's just not inverted. So what that means is, from the reactive point of view, a capacitor is the opposite or the inverse. X to the minus, so XL is equal to XC to the power minus 1. It's the inverse. Just one upon the other. But what does this tell you? What does this tell you? Well, what variables do we have? We have C. Sorry, that should be L there, by the way. I'm sorry about that. We have C, but C is fixed. There's trays and trays and trays of them, but once I pull one out of the tray, and I put it in my simulator, or I put it on my circuit board, it's fixed, it doesn't change, right? So if C is fixed, I is fixed, 2 is fixed, 1 is fixed, the only variable I have is F, frequency. Where did the 2 pi come from? Anyone? Maths, yeah. So the 2 pi is a simple circuit, yes. So it comes from radians. It's a more convenient way of representing waveforms, is to do it in radians, because the maths that follows is greatly simplified by doing it. But you can almost neglect that. You just call that omega if you want. So 2 pi f is just this. And you'll see that quite often in textbooks and so on, because people get fed up of writing 2 pi. So it just becomes overkill. What does this equation tell you about the capacitor? Remember, the only variable, let's assume that C is 1. It's a whole farad, huge, but let's just assume that C is 1. What happens if we make F bigger and bigger and bigger? So let's make F incredibly small to start with. Well, what's incredibly small? 0, right? 0 is incredibly small. Yeah. Well, we can't do that, because otherwise we have 1 upon 0, divided by 0 problem. So let's just say it's 1. If we have that, we've got 1 upon 2 pi times 1 times 1, we've got 1 upon 2 pi. So what does that tell you at low frequency?
The higher the resistance the capacitor opposes, the position the capacitor will provide to the AC circuit will be higher at the low frequency and low at the high frequency.
Exactly, yes, but let's not get too far ahead of ourselves. So if we say that F in this case is 1, so at F equals 1, and we're assuming that C is equal to 1, 2 pi doesn't change all the rest of it, the effective resistance, or the capacitive reactance that we have is 1 upon 2 pi, and that's it, right? Because F is 1 and C is 1. Yeah? That's F equals 1. Now let's make F really big. Let's have 1,000,000, shall we? 1,000,000 is pretty big. So what we end up with, if we do that, is we end up with, so F equals 1, that's that case there. So F equals 1,000,000. So we're at a megahertz now. Well, what do we have there? We have XC is equal to 1 upon 2 pi. Remember our C is 1. 2 pi times 1,000,000. I'll just write million. Well, 1,000,000 times 2 pi is a pretty big number. It's 2 pi millions. What's 1 divided by 2 pi millions? Really small, right? So what that means is that this one here, XC, is small. And in this case here, XC is quite big. I'll leave you to work out what quite big actually means. But you can see, right? So what that means is that capacitor, at low frequency, it blocks. Let's write that. Low frequency it blocks, and at high frequency it passes. It lets it through. That's a piece of magic. That's exactly what we want to build some really, really complicated circuits. We've got something that behaves differently according to frequency. Forget the capacitor, it's a fixed value. So that's magic. So then that means we could interchange this with any one of these and we could build a filter. We'll be doing that next week. I won't cover that ground again. Okay, so what's the takeaway? Capacitor blocks low frequency. A capacitor passes high frequency. Yeah? Got that? Well, what about the inductor?
It blocks high frequency bar and allows low frequency bar.
Exactly. So it's completely the opposite. But let's just have a look at where that came from. So if I say, same as before, so if I say F is equal to 1, so then XL is equal to 2 pi, F is 1, L is 1, so XL is what? 2 pi, yeah? So if the frequency is low, lets it through. But if the frequency is high, it means that the reactance or the equivalent resistance is also very high. So your inductor will let through low frequency, but it will block high frequency. And why? It's only a bit of wire. I can make an inductor, I can go and get a piece of wire, wrap it around my finger and solder, put some solder on either end, put it in an inductance meter, and it will tell me it's got inductance. It'll tell me that it's got a reactance. It'll tell me how much that is in ohms. But where's it coming from? How can I turn a straight piece of wire with no resistance, or maybe a hundredth of an ohm or something, how can I turn that into something that maybe at a megahertz has an impedance of hundreds and maybe even thousands of ohms? Where does that resistance come from? Electromagnetism. So what you're doing is you're taking that energy, and because it's in a coil, you're creating a magnetic field around it. Now, the more that changes in time, the bigger the magnetic field, so the bigger the apparent resistance. But you don't even need to remember that. All you need to remember is an inductor lets through low frequency. At low frequency, it's just a wire. But at high frequency, the coil part of it starts to come in and you start to see this kind of magnetic field happening around it. So a capacitor, what? Tell me. What's a capacitor do low frequency? What does an inductor do at low frequency? What does a capacitor do at high frequency? What does an inductor do at high frequency? Exactly the opposite, see it? Yeah? That's the magic behind it. So anything that I do that's and this is really just a lead into next week, but I'll give your brains a rest after this.